Oh, hi. Sorry, I was busy. Okay. Uh, Good evening, everyone. So, welcome back. Let me share my screen. So, I believe we were working on the center of mass. And in yesterday's video, I think I had just made a revision on what we had looked at in center of mass. Acha, okay, fine. So, okay, let me go back. Yeah. So towards it, we had asked a question about whether the center of mass can also have a velocity or not. So that was yesterday's video. So then we looked at, okay, how do we get a center of mass velocity? And today, okay, so yesterday we have seen like how do we get the center of mass velocity? And then these are some of the examples we have seen. And today, let us look at one more example with the same topic, but the question here is a little bit different. Okay. Let us do this. Just give me a moment, guys. Something wrong. I'm not able to move some of my panels over here. Okay, fine. Two blocks of masses M1 and M2 are connected by a spring or spring constant K and are placed on a frictionless horizontal surface. So I have two blocks. I will write because I need some space. I will write two blocks like this. This is in continuation with the old problem only. Let me just go back to this. Okay. Anyway, I will explain this. Okay. So two blocks are kept like this at spring constant K. Spring constant K. These are having different masses. M1, M2. Okay. The block of mass M2 is given a sharp impulse. So you are giving this mass a sharp impulse. That means what? You're just hitting it like this. So it acquires a velocity V0 towards right. So as it moves forward, it moves with a velocity V0. Hey, how come here? See, you're having a mass M2, you're giving a velocity V0. See, initially, what does it say? Okay, that doesn't have any velocity. So this has so you're giving a velocity V0, right? Okay, find the maximum elongation the spring will suffer. See, all are on the frictionless surface. So as a result of it, what happens when you're giving a velocity here? This object will start moving like this. This object will start moving like this. Then this will extend the spring. Okay, so what will happen after some time? Let us say this is my M1. Then this will now become extended like this. And this will become my M2 here. So as a result of it, M2 will be moving further, M1 will be lagging behind. It will not be fixed over here because there's no friction. So this will also move. This will also move. Okay. Now, what would be the velocities of these two? So let us say if this is V0 initially when I hit it, definitely after some time, because this is the energy I'm giving it, the part of the energy will go to this, will extend the spring, and part of it will go here, such that the sum of these two energies is equal to this energy. So the mass M1 will not get the same energy as what is being given here. So as a result of it, might be this velocity might be different as compared to this. This is what we need to understand. Okay. Let us see. Okay. So at one point of time, you observe that there will be a maximum extension. Okay. How do I get it? That's the question here. So the student response is like this: spring energy due to elongation. Let us say at some moment of time, some point of time, the spring completely expands, and the total energy in the spring is half k squared. This is due to the kinetic energy of the both masses M1 plus M2 into V1 square by 2. When it extends, okay, then what can happen is these masses are also moving with a velocity, which is definitely not equal to V0 because V0 was the velocity at that instant. Okay. And this should be equal to V1 square. Let us say V1 here. So sum of these kinetic energy is equal to the spring energy. I do not know. Okay, how do you equate these two? But anyway, this is what is the response I had got in one of the papers. Applying the conservation of momentum, we get M2V0. I made a mistake here. M2V0 is equal to, there's no equal to here, M1 plus M2 into V1. What is this now? Okay, this is the momentum, initial momentum. Okay, before the masses started moving. This should be equal to M1 plus M2. Okay, if we assume that both of them are moving at the same velocity into V1, and thus we got the expression for V1. Now we will substitute V1 here, and as a result of it, and equate these two. Okay, and I will write half kx square is equal to half into M1 plus M2 into, instead of V1, I'll write this as m2 square v0 square divided by m1 plus m2 the whole square. I'll write like this, and then this half also goes away. So I get the value of x to be equal to m2 v0 divided by square root of k into m1 plus m2. This is what is the expression I get. So student thought, okay, this is right. And he was arguing with me. I done everything correctly. I applied center of mass concept. Everything I've done correctly. And you are not giving me the marks. Now, where do you think the mistake lies into? The mistake lies at this point. So where is it? At this point. How do you equate this equation to this equation? Quite difficult, right? Is it the kinetic energy of some of the masses was responsible for the spring elongation? No. Okay. That's why smaller points, okay, you have to be, every point, everything you need to be very careful. Otherwise, this is what will happen. Now, let us solve this. I hope you have understood the misconception here. The misconception is equating the energies. Okay. Now, but the question here says, can the center of mass have a velocity? Definitely, center of mass will have a velocity. We have seen it earlier also. We're continuing with this one. Okay. So now, what we will do is, we will first find out, you are given some velocity here, and as a result of it, m2 went away. Let us apply your COM. This part of it is correct. m2 v0 is equal to m1 plus m2 into v1. Or instead of writing v1, okay, this is the correct solution I'm doing. Okay, correct solution which I'm doing. I'll write, instead of v1, I'll write this as vcm. Because what is that v1 over here? m1 plus m2 are moving together. And why should this be vcm? That's the question we need to ask. Now, see, when this m2 is moving apart from here, m1 will slow down. Okay, at one particular time, m2 and m1 will have the same velocity. When they have the same velocity, then the spring will have maximum elongation. Remember, we have seen this in one of the previous problems also. Okay, the spring. Okay, so to first begin with is spring will have maximum elongation only if the relative velocity between the masses is equal to 0. Which means what? If this is moving at a velocity v1, this is moving at a velocity v2 after some time. Okay. So initially, this moves like this also moves slowly. And then after some time, both the masses will be moving at the same velocity. In that case, the elongation will be maximum. Okay. That is what we need to look at. Find the maximum elongation. So therefore, so when they are moving at the same maximum elongation, this is similarly equivalent to something like you have an object M1, you had a marble M1, you had a marble M2, and you hit this one here, you hit it like this over here, or maybe you hit this one here. Now this went collided with it, and finally both of them joined together. And they started moving at a uniform velocity. Correct, right? Inelastic collision. Okay. Here we are not doing inelastic. Okay. So here, because there's no friction, no energy is being lost. But here the energy was lost, but here this energy is given to the spring. Okay. In this aspect, he has done something like this. Let us see where does it go wrong once again. Now, VCM is equal to, now what do we write here? We write this as M2 V0 divided by M1 plus M2. We have got an expression for the center of mass velocity. Center of mass is not lying in this object or this object. It could lie in between. It could be lying over here, whatever it is. What's the next step? The next step is you are not using your force equations. See, every problem in physics can be solved either by force equations or by energy equations. Now here, we do not have time factor here. So you cannot use force. Okay, you cannot use your Hooke's law. The only thing that you can use is energy. Now what is that energy equation? Energy equation tells you kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. Right? What is kinetic energy initial? Which means when the system was like this, okay, you applied a velocity. So kinetic energy was seen to be half mv0 square. What is potential energy initial? This was not at a greater height with respect to Earth. Okay, it is surface on the Earth. So therefore, 0. What is surface? What is the potential energy of this? 0 once again. What is the potential energy of the spring? Spring was not extended. It was in its natural length. 0. 0. They should now be equal to kinetic energy final. What will happen to the kinetic energy final? Can you think about what is the kinetic energy final? They should now be equal to half. Just a moment. Something is wrong with my system. Let me just wait for a moment. I will just check it. Okay, I think it's fine now. Okay, now I was talking about what is the kinetic energy final. What is kinetic energy final? See, both the objects are moving with the same velocity. That's what I said, right? So it should now be equal to half into m1 into what is the velocity of the first object? First object was moving with the velocity v1. What is that velocity v1? Vcm, right? Gm square plus what is the velocity of second object? That's also moving with the same one. Half m2 into vcm square plus then what else do we have? Plus what is the kinetic energy of the spring? It should be equal to half kx square. Right? Now let us start with this. So we have half mv0 square minus see what is this m here? Is this m? This is m2, right? Oh my god, see. We mix these suffixes, that's what will happen. Okay. M2, I'll do one thing, I'll take half common into half into m2 v0 square minus m1 plus m2 into VCM. What is VCM? VCM is given here. Okay, I'll substitute this. M2 V0 divided by M1 plus M2, the whole square is equal to half k square. Wow. Now see, somewhere we have got a better pattern. This half and this half cancels. Now what do we have here? Let us expand this. So this will imply, what do we have? V0 square common here. Let us take V0 square common. V0 square into M2 minus of M1 plus M2, M1 plus M2 into M2 square divided by M1 plus M2 whole square. See, this I am expanding. Okay. Okay. Is equal to kx square. Kx square. So this and this goes away. And I can remove this M2 common. I need some space. M2 V0 square into 1 minus M2 divided by M1 plus M2 is equal to kx square. Or once again, how do I write? If I take the LCM here, this will become M1 plus M2 minus M2, which will become M1 here, right? So which will now be equal to M1, M2. See here, I'll have M1 here on numerator. M1, M2 into V0 square divided by M1 plus M2 is equal to kx square. I don't have space. I'll do one thing. I'll just write down the whole thing over here. I have some space here. Okay. Try to minimize it, but unfortunately not possible. So now kx square is equal to m1 m2 v0 square divided by m1 plus m2. What else do I need? I need the value of x. X is equal to m1 m2 divided by m1 plus m2 into k. Okay. Into square root into v0. Okay, I think I have included everything here. Yes, right. So thus, what did we get here? We got an extension. We got a formula for the maximum elongation of the spring, which is like this. Okay, that's what was the earlier result. We got something like this. Thank you, friends. I hope you have understood the concept better. So if you have understood it, do like it, share, and subscribe to my channel for more updates. And we will see some more about center of mass in the next few videos. Thank you.